Hello, we are Team Waffles from Raffles Girls' School, and this is our presentation for RoboCupJunior Singapore Rescue Line U19. Our team consists of Claire, Megan, Shi-Han, and Jovelyn. For this competition, there are 4 tasks that the robot must complete in order to finish the mission. Firstly, we'll be sharing about how a robot is able to overcome speed bumps, ramps, and seesaws. We chose to use tracks instead of a 2 or 4-wheel drive base because tracks have the most point in contact with the ground. Unlike wheels, tracks provide a larger surface area in contact with the ground, especially when the robot crosses speed bumps, offering more traction and more even weight distribution. This design enables the robot to overcome obstacles like speed bumps while evenly distributing its weight when navigating seesaws, reducing the risk of toppling over.
Next, we'll be moving on to how a robot is able to line track and detect the green squares. For line tracking, we use 2 imagery color sensors that are mounted 2 cm above the net so that it will not get blocked by the speed bumps and 4 cm apart. This is the distance between one line to ensure that the sensors are on either side of the black line, which is ideal for the robot to correct itself back on the line precisely. The color sensors are placed near the robot's center of gravity, and this is important since the robot is using tracks to move, and the color sensors will determine when the robot starts to have a change in movement. The small distance between the sensors and the robot's center of gravity allows the robot to track the line closely and decrease the chances that the robot will lose the line. Next, the green squares. The robot will first check if one sensor is on green. If only left is on green, the robot will single line track with the left color sensor. If only the right is on green, the robot will do the same with the right color sensor. However, if both sensors are on green, the robot will make a 180-degree turn and continue line tracking as normal. Furthermore, we decided to use a single line track code after the robot detects a green square, instead of making the robot turn by a constant degree to ensure that the robot won't turn too much and overshoot the line. This could happen in the above possible cases. We chose to use the HSV values instead of the RGB values to detect the green, as we have found it to be more accurate and efficient. The RGB values only takes into account how much red, green, and blue is reflected with a small range for each color, which can also differ greatly according to the lighting or type of green. Compared to this, HSV gives the hue, saturation, and value. As shown in the picture above, everything in the range of green that is not white and not black, we can determine that the color is green. Thus, we can narrow down the range of greens and it can detect for green accurately. Originally, we had tried a method of checking for green squares only after the robot detects a double black junction. However, this would not work for a few cases. For example, for a Y junction, the robot may sense a double black junction too late and move back too little, hence it would not detect the green square. For T junctions, the robot will also not detect the green square since there is no double black junction after the green square to trigger this loop.
To do obstacle avoidance, we made use of 2 time-of-flight sensors. We did not use a color sensor because if the obstacle was black, the robot may not be able to sense it in time. The TF sensor uses the flight time of light to measure the distance to an object, in this case, the robot's distance to an obstacle. Compared to ultrasonic sensors, TF sensors are much more compact and also allows for a greater range and higher accuracy of values. We decided to use 2 TOF sensors instead of 1 to allow the robot to avoid objects of any size by object tracking. Once the front sensor detects an object, the robot turns and stores the initial value of the side TOF as the initial distance. Then, we take the measured values of the side TOF subtracted by the initial distance multiplied by a constant for the turn rate to ensure that the robot maintains a constant distance away from the obstacle. This distance is neither too far or too near, allowing the robot to move in an arc shape around the object. After that, the robot turns back to the line and continues to line track. Lastly, we'll be sharing about how our robot gets past the evacuation zone. Our robot uses its floor-facing color sensors to detect the silver tape, signaling the start of the evacuation zone. However, if the robot does not enter the evacuation zone at 90 degrees, the subsequent movements will not be accurate. To overcome this issue, the robot waits for both sensors to detect silver before entering the evacuation zone. If only the left sensor detects the silver tape, the robot will turn to the left slightly until both sensors are on the silver tape. The same goes for if only the right sensor is on the silver tape, the robot will turn slightly to the right.
Once in the evacuation zone, the robot needs to find and identify its victims. The robot maneuvers the evacuation zone using a spiral pattern, which we realized would take up significantly less time compared to the snake method. We made use of the robot's side-facing time-of-flight sensor to ensure that it is always at a constant distance from the walls of the evacuation zone and can constantly move in a straight line. This distance will be increased according to the number of turns. To pick up and deposit the victims, We decided to use a grab and lift claw so that the robot can collect and lift the ball with just one motor. We also tied rubber bands around the claw to increase the friction between it and the ball when it's being picked up. The claw picks up the balls before depositing them in the sorting mechanism. If the ball is silver and the victim is alive, it will get stored into the channel on the right. If the ball is black and the victim is dead, the ball will get sorted to the channel on the left. After the robot picks up all the victims, it will then locate the position of the red and green corners to deposit them. When the robot locates the corners, it will move backwards against the corners so that the tray can pivot upwards and deposit the victims in the respective corners. After depositing the victims in the correct zones, the robot needs to find the exit. In order to find the exit, the TOF sensors will constantly sense the distance between the robot and the wall. If both the front and side-facing TOF sensors detect a short distance from the wall, the robot will turn. Eventually, when the side-facing TOF sensor senses a larger distance, it means the robot is at the exit. In another case where the side-facing TOF already senses a distance of more than 1.2 meters, the longest distance from both walls, it means that there is an opening in the walls of the evacuation zone, which is the exit, and the robot will travel there directly.